You can test it out right now for free. Finally, you have a way to simulate your rockets that gives you the true information that you need to be successful. And the best part is that you don't have to walk after your rocket after it comes back down to the ground. Experience the fun. Test your rockets right now at RockSim.com. Most Rocketeers seem satisfied with just being told how high their rocket flew, and that's a shame. How did the rocket get to that point? That is what you should really be concerned about. The story of your rocket's flight is just not a peak altitude number. The real story is the trajectory path that your rocket takes during the flight. Does it go straight up or does it arc over? Does it spin as it ascends? What happens once the recovery system is deployed? Where does the rocket go? How far away does it land? Will it touch down in a location where you can easily recover it? These are the answers that you can get using the Launch Visualizer. It is an app on the RockSim.com website, and you can test it out right now for free. Finally, you have a way to simulate your rockets that gives you the true information that you need to be successful. And the best part is that you don't have to walk after your rocket after it comes back down to the ground. Experience the fun. Test your rockets right now at RockSim.com. Most Rocketeers seem satisfied with just being told how high their rocket flew, and that's a shame. How did the rocket get to that point? That is what you should really be concerned about. The story of your rocket's flight is just not a peak altitude number. The real story is the trajectory path that your rocket takes during the flight. Does it go straight up or does it arc over? Does it spin as it ascends? What happens once the recovery system is deployed? Where does the rocket go? How far away does it land? Will it touch down in a location where you can easily recover it? These are the answers that you can get using the Launch Visualizer. It is an app on the RockSim.com website, and you can test it out right now for free. Finally, you have a way to simulate your rockets that gives you the true information that you need to be successful. And the best part is that you don't have to walk after your rocket after it comes back down to the ground. Experience the fun. Test your rockets right now at RockSim.com. Most Rocketeers seem satisfied with just being told how high their rocket flew, and that's a shame. How did the rocket get to that point? That is what you should really be concerned about. The story of your rocket's flight is just not a peak altitude number. The real story is the trajectory path that your rocket takes during the flight. Does it go straight up or does it arc over? Does it spin as it ascends? What happens once the recovery system is deployed? Where does the rocket go? How far away does it land? Will it touch down in a location where you can easily recover it? These are the answers that you can get using the Launch Visualizer. It is an app on the RockSim.com website, and you can test it out right now for free. Finally, you have a way to simulate your rockets that gives you the true information that you need to be successful. And the best part is that you don't have to walk after your rocket after it comes back down to the ground. Experience the fun. Test your rockets right now at RockSim.com. Most Rocketeers seem satisfied with just being told how high their rocket flew, and that's a shame. How did the rocket get to that point? That is what you should really be concerned about. The story of your rocket's flight is just not a peak altitude number. The real story is the trajectory path that your rocket takes during the flight. Does it go straight up or does it arc over? Does it spin as it ascends? What happens once the recovery system is deployed? Where does the rocket go? How far away does it land? Will it touch down in a location where you can easily recover it? These are the answers that you can get using the Launch Visualizer. It is an app on the RockSim.com website, and you can test it out right now for free. Finally, you have a way to simulate your rockets that gives you the true information that you need to be successful. And the best part is that you don't have to walk after your rocket after it comes back down to the ground. Experience the fun. Test your rockets right now at RockSim.com. Most Rocketeers seem satisfied with just being told how high their rocket flew, and that's a shame. How did the rocket get to that point? That is what you should really be concerned about. And we're live! Hello, I'm Tim Van Milligan. This is RockSim Live. Hopefully this is going out. I'm trying to watch two computer screens here, see what's going on. And there are people in the room. Cool. Okay, I can see that it's live on YouTube, but I don't know if the sound is good. So let me know if the sound is good. Yes, as I said, this is RockSim Live. This is where we talk about the RockSim software. We also talk about RockSim Pro, which we did a lot last week, and the Launch Visualizer. Carlos says audio and video is okay, so everything is going well. Yeah, what's going on? We have a new rocket kit that we're going to be releasing next week. This is a 1/15th scale model of the Black Brant VC, which is the Black Brant 5C. This is a rocket that NASA has flown over 1,000 times from Wallops Island in Virginia. And this is probably one of the most accurate models of it. We even include the rail guides on top. Then we got all kinds of little decals. The thing about the Black Brant is I don't think they've ever flown the same exact version twice, because each of them has its own little payload. And so like from here down is the same, but from here up it changes a little bit. So it's kind of generic, so we gave you generic decals for the upper part. It's also got rivet decals for down there at the bottom. Yeah, it will fly on 18 millimeter motors. It's 30 millimeters in diameter. Yeah, or 29 millimeters in diameter. And like the real Black Brant, it has, it's two sizes of body tubes. It has the big tube here and a smaller tube here, and it kind of steps down a little bit. So that's the Black Brant. It is going to be available on Tuesday of next week, which I'm not sure what the date is. But here's what the kit's going to look like. Yeah, our goal this year is to produce 12 kits, and I think this is number 5 already, so we're ahead of the schedule. And we got some really cool stuff coming later too, but this is our latest one. 2 weeks ago, if you see over here in the back, we released the level 2. That's an all fiberglass, 4-inch diameter, close to 6 feet tall. It is for a level 2. It's definitely high power, 54 millimeter motor mount in that one. So if you're looking for a high power motor or a high power rocket, that's the one. We have Carlos here, and he's from Marietta, Georgia. We have Ben Reedford, says hello. We have Chris's Rocketry and More from Golden Valley, Arizona. And he says, I hear you. Okay, so this is RockSim Live, so we're here to talk about RockSim. So if you have questions about RockSim, this is your opportunity to voice those. And we also have Stuart from Bear, Vermont. Awesome. I'm gonna kind of just kind of close that one down. You can see I got a monitor over here. You can actually see my table, which is made out of cardboard. Yeah, so let me change screens and go to the desktop. So here is RockSim. And I've got just a generic rocket right here. Let me open up our website. I want to go to Microsoft Edge, and not now. Let's go Apogee Rockets, Bing search, here we go. Apogee Rockets, there we go. This is our website, apogeerockets.com. We're doing RockSim Live, so if you see this right here, this is what we're doing right now, live training for RockSim. If you click on it, it brings you to our archives, and you can see what we talked about last week. We were designing finless rockets, and then one-fin rockets and two-fin rockets. So that was a lot of fun, a lot of good questions last week. And so you can see what we've talked about in the past. If you wanted more information about RockSim, and if you've never used it before, go to the How To and Guides menu here at the top, come down to Software, and you'll see the RockSim free trial. You can also figure out what it is, what is RockSim, the features, the frequently asked questions, system requirements, version history. Here again is the RockSim Live training. We have other video tutorials here. Yeah, so that is kind of what's on our website about RockSim. So you kind of get you up to speed if you've never used it before. I did have one question that came in from Carlos, and he was asking about there was a rocket that Estes made a long time ago called the Dude. Let me see if I can find a picture of the Dude. Search the web. The Dude rocket from Estes. There it is. You can't barely see it, but it was a balloon rocket, and down at the bottom you would put a D12 rocket motor in it. I don't know if I can show a better picture of this or not. It was only available from 2001 to 2003, apparently, and it had some problems. It was made out of a Mylar balloon. It was 7 feet tall. It was listed as the largest rocket that Estes had ever made, which might be true, but the problem was the ejection charge of the rocket motor, that pushes the parachute out. Well, it would throw a lot of sparks forward, and those sparks weren't supposed to hit the Mylar balloon, but they would. And when they hit them, it would just burn a hole right through the Mylar, release all the air, and your rocket would come down like a streamer instead of looking like a rocket. So that it had a problem. That's probably why it was discontinued. That's just my guess, because I'm sure it sold a lot. So Carlos's question is, what would happen if you had a rocket like that and you filled it with helium or hydrogen, something that has less density than air? Could you do that in RockSim? And if you could, would that make a difference on streamer duration? So let's find out. So we can take any rocket. Do I want to take this rocket? So basically what I want to make kind of like the Dude rocket, where I want to make the nose cone and the body tube out of something super lightweight. Basically, how do you fill something with air that's already a tube? So we can't close it off and hold the air pressure inside in RockSim. The only way that I can think of to try to simulate that is to change the wall thickness of parts and change the density to kind of simulate what the rocket would behave like as if it were filled with helium or hydrogen. So how would you do that? Well, you'd start by going to the rocket menu, and we're going to edit the database, and we're going to edit the database of materials. Okay. So here's the database of materials in RockSim. All right, and we might have Mylar in here already, but we're going to have to combine materials because we have an outside shell made of Mylar, and then internally it's filled with helium. So basically we got to create a new material that's a combination of both of those materials added together. This is how engineers do things. They look at the constraints, and then they try to find a workaround around them, even though you can't fill the rocket with air or fill it with helium, something that's lighter than air. Just trying to think if you could or not. You could probably put a mass object inside the rocket, but I don't think you could put a negative mass object in. That would be like the cheating way. So that would be like the first way. Let's try it. So we have a nose cone here. And inside the nose cone, let me cancel that. Inside the nose cone, we're going to put a mass object. And I wonder if it will allow us to have a negative mass object. So when you create a mass object, it always looks in the database. We're going to cancel out of that. So right now it's putting the mass object here at the nose. And we're going to move it back here. And let's call it helium as the name. I'm just going to leave it at 0 for right now. I'll click OK. Okay, so it says it must be greater than 0. So there's no way we're going to be able to put in a minus, like 5. Probably going to get an error. Okay, so we tried that. That didn't work. Save your changes? No. Okay, so now we're back to a nose cone without a mass object in it. So now we can't put a negative. So now we do have to go back to creating a part. So let's go to the rocket menu. Let's create a new material in the database. Let's see if we can do that. So I'm going to go, first I want to look up some masses of things. Add new. I don't think it's going to allow me to have a negative density. But let's try. So let's call it helium. And the density units, pounds per foot cubed. And let's call it a minus 2.0. Let's see what happens. Fixed dimension, none. Fixed dimension, this is, say you have a piece of balsa wood and you wanted to add it into your database. And so you could set it up to have the weight per a dimension. So the longer you made the balsa wood, it would automatically calculate it. That's kind of what that means. And then if you did have a fixed dimension, what are the units? And you can, have inches or millimeters or kilometers or whatever. And then this is rocketry use, and we need to check this box. That means, yes, we can use it in rocketry. We'll use it for body tubes and nose cones. So, oops, nose cones is right here in this column. Yeah, and then let's click OK. It took it. Okay, so let's make our nose cone out of helium. So I'm going to go to the nose cone. And currently, right now, it's 0.178 pounds, which is 81 grams. And let's change the material to helium. So now helium should show up in our list somewhere. It's at the very bottom. So if it worked, if our new density worked, this component mass should be a negative number. Oh, it says mass override is on. So before I do that, let me go to the mass override and uncheck that. And then go back here to general. Okay, so it's still calculating the mass at 81 grams. And if we change the material to helium, and okay, look at that! We did it! It worked! It's a minus 2.47 grams. That is cool or what? And then you would do the same thing for, let's click OK there. Do the same thing for the body tube. So material, that should be in our database, helium. And again, this is a negative number, so that's good. But let's look at it in 2D. So the problem we have here, we do have this parachute up here. I'm worried that our center of gravity is going to be really far aft with these components that are super lightweight. But let's try it. So let's get rid of those strike fins. So we'll go to the, they're in the body tube, so let's find those fins. So I'll just click on them over here, and it will highlight it here, and I'm going to delete it and say yes. I got this mass object right here. What's that? That's the shock cord. Yeah, we probably need that. Let's see, what's that parachute? This is a 24-inch parachute. Well, let's make that a lot smaller now that our rocket weighs a lot less. Let's make it like 10 inches. And click OK. Okay, is our mass override on? Use the, yeah, see it was on. Let's turn that off. And once we turn that off, this mass will change, and the center of gravity will change as well. Oh, see, this is what I was worried about. Because everything is negative weights up here in the front, our center of gravity is way back here. And when we put a rocket motor in this, so we go up here to the rocket motor and go to choose engine, and let's put a D12 in there. It's this East. Let's sort this by engine code. Let's show only that match. Okay. Okay, so there's a D12. Let's make it a D12-7. Let's click OK. And parachute deploy a maximum ejection, simulation 800. Starting state, we can go, let's make this, I don't know, 60 inches, which is 5 feet. Launching straight up. And this has, let's make this 700 feet, because that's what I usually run at, 700 feet. And let's bring the wind down a little bit, down to 5 miles an hour. And let's go click OK. So this rocket is showing unstable. This is the problem with things that that have no mass at the front, or negative mass. But let's launch it anyway. So flight profile, I expect this one to go unstable. And sure enough, it did. And it does land. It does have some mass because of these rocket motors here in the back. It only got up to 777 feet. Because it went unstable. We do definitely need some weight in the front of the rocket to make it stable. The dude had some huge fins on the back. That would certainly help. And if you wanted to change your fins, you know, you can come here to the rocket design components, edit the fins. We'll sweep them aft, kind of like the dude did. You see when I'm sweeping them aft, the center of pressure is moving back, and then we make them semi-span, make them bigger, and that helps, but it's still not far enough back. Let's move the location further back. Let's make it, I moved the slider as far as I can go, but I can still type in a number. So I'll type in 24 inches. Okay, so now our center of pressure is behind the center of gravity, and it should be stable. I can move it a little bit forward. I just want to keep it stable. And click OK. The weight of our rocket, let's see, is we're at 0.14 pounds. Let's change the units. So to change the units, go to Edit, go to Preferences, and then here's units, and let's change this to grams instead of pounds. And velocity, let's go back to miles per hour. All right. Okay, so we're at 64 grams. So this is pretty cool. I didn't think we could have a negative mass, but we certainly can. Let's launch it again. So look at the flight profile. So there's the rocket sitting right there when we launch it. Oh, it still went unstable. And it's we're hitting the ground long before we got up to 80 feet, even though we're still stable. Let's move those fins back just a little bit more. See if we can make this thing stable. I'll go back to 24. Click OK. Flight profile. Let's launch it again. I'm going to cheat and see. Okay, so now we're getting up to 800 feet. So now the parachute should come out. And we did get up to 800 feet, 900 feet. And there's our parachute. And this thing, because it doesn't only weighs 64 grams, it's going to take a long time to get down to the ground. We're well over 60 seconds down to the ground. So I hope that answered your question, Carlos, is can you make a helium-filled rocket? And we can, although we did have to do a lot of work. We had to create a special new material that had a negative density and that allowed us to make a rocket that was helium-filled. And I just guessed at what the density is. You'd have to research that yourself to figure out what kind of mass or what that density would be to be able to have a negative weight rocket. It is hard to make those rockets stable, though, as you saw, because the weight up here in the front is so light. In order to a rocket to be stable, that center of gravity back here has to be in front of the center of pressure. And the only way that we could do that was to slide our fins off the rocket. So move them way, way, way back. Carlos says, did we get an Argentina launch site from last week? And that's a good question, Carlos. I vaguely recall getting an email from our system saying that there was something, somebody submitted a launch site. We did get Carlos. The answer is no. We did not get a launch site in Argentina. We were hoping. I think he's tried to submit something, and I looked at it, and it was the launch site that he submitted was in Africa, which is not in Argentina. So I think he just didn't know how to submit one. We have Bill Shebeck from Mojave, California, Fatbank from Texas, Rosa from Ottawa. Fatbank says, if you air started 4 of 7 motors, can RockSim maximize an altitude for a lock precision ultimate? Okay, we can try. That's a good question. That's a good question, Fatbank. First, we need to find a lock ultimate. So I'm going to the design folder. Let's see if it's already in the. Yes, it's in your database. So if you open your database, you will find it in there. So this is what the lock ultimate looks like. And if you look at the back, it's got a cluster of 7 engines. So his question is, if you air started 4 of them, so I'm assuming he's like this one, this one, this one, that one, and then you lit 3 of them on the ground, can you maximize altitude for Lock Precision Ultimate? Okay, so normally in RockSim there is a there's a motor recommendation button, but that's not a motor maximization button. The motor recommendation button is, if you open it up and you click on this button here at the top, this is like the base of the rocket with 2 arrows pointing down to the launch pad. That's what that looks like. And if you click on that, there's a button right here down at the bottom that says recommend motors, and then you can see right now it's grayed out. I can't click on it. And the reason is that it only works on rockets that have a single rocket tube in the back. This one has 7 tubes, so it can't recommend, because we talked about this one before. There's so many permutations available that we can't recommend just a single motor, because in fact, we did a newsletter article about that. And I can show you that. If you go to the Apogee website and you go to How-To and Guides and then click on the Picoflight newsletter, and you go to all newsletters, and we want to do a Control F, and that brings up the Finder box up here. And let's type in the word cluster. Issue number 583 is the motor options for clustered rockets. So how many could you put in your rocket? And this was written by Rick DeFossis. And Rick wrote this article after watching RockSim Live. And he goes through the math of all the different permutations that you could have, and you'll quickly see it's a factorial number up here. So in the flamethrower rocket, which is a 2-engine cluster, there are 2,346 different motor combinations that would work. And so for RockSim to run all those, it would just take forever. So RockSim can't recommend a motor. So how do you optimize or maximize the altitude? Well, I guess you need to put in some constraints here, like say, you could have a constraint on, the rocket motors have to be under, a certain length, or no motor that costs more than X number of dollars. Because in the 29 millimeter motors, if we click on choose engine for a 29 millimeter, you can see this is the list. It starts with an Estes E16. And, and I can scroll and scroll and scroll and scroll and scroll and scroll. And, I'm in the H's and I motors. There's well over probably 60 or 70 motors that we could choose from. And so if you wanted to maximize the altitude, I mean, the best thing to do is use the ones with the most total impulse. So if I sorted it by total impulse, with the biggest one on the bottom, 384 Newton seconds of power is the I-243. And so if I load that in there, and we'll have to choose custom. Let's choose, I don't know, 20 seconds and use, and click I forgot about it. I gotta choose the ones first. Okay, so we're going to choose an I-243 white. Click OK. So it loaded it there, and I'll say load all. So now it loaded all the motors there. And if we launch it, we'll see how high it goes. It went 9,094 feet with all 7 I motors lit on the ground. Now, if you air started 4 of them, how to do that? We'll go back up here to prepare for launch. And so they're already loaded, and we're going to have an ignition delay on 4 of them. Let's see if I can make this bigger for you so you can see. So right now, this first motor is right there. If I click here, that one is right there. This one is right in the middle, is right there. Okay, so those motors we're going to light on the ground, and then these 4 right here, those 2 and these 2 at the top, we'll do an ignition delay on them. So now the question is, how long of an ignition delay do you use? You could say, let's start with 5 seconds. So that one's 5, that one's 5, and that one's 5. So at 5 seconds after liftoff, those motors are going to ignite. And if we launch that one, you can see we got more altitude. Now we're up to 11,856 compared to 9,000. So we gained, almost 3,000 feet by doing an ignition delay, so air starting. And so what's the optimal ignition delay on your motors? And it actually turns out that the ignition delay, so let's go look here at the graphs, and we'll do time as our x-axis, velocity, and we'll also display the thrust. Where's thrust? Did I go past it? Here it is, thrust. And let's go when the rocket reaches apogee and plot that graph. Okay, so on this graph, the blue lines, which are kind of faint, which I think you can see, is the thrust of the motors. So here is the thrust of the first 3 motors. They burn out, and then there's 5-second delay. And then these motors start right here. And you get burnout right there. So the velocity of the rocket, it takes off really fast, and then it starts coasting, and then it starts burning again. And the optimal delay for this configuration is when the velocity drops down to 0. And so if we kind of extrapolated this curve out here, we would probably get to like somewhere like 20, let's try 23 seconds and see what happens. So I'm just taking this curve right here and just kind of extrapolating out. And we'll see if that will change our altitude. Okay, so we're back onto the motors. And let me make this wider so you can see it. So we have these 4 down here have the ignition delay of 5 seconds. And we're going to change these to 23 seconds. So hopefully the rocket, as it goes up, it's going to coast after those first 3 burn out. And we want it to coast until it stops. And at that point, take off again. And so let's launch it. Oh, and look at this. We didn't go as high. And so what happened? So let's take a look at the flight profile and see if we can determine what went on. So there's the rocket taking off. The motors burn out. The rocket's coasting upwards. We're at 8 seconds, 9 seconds into the flight. 13 seconds. Okay, so here's the problem, is our rocket's turning sideways. And now it's falling down, and now it's firing those other motors. So we hit our peak altitude, but the rocket arced over. And so when we fired the next set of motors, it was going in the wrong direction. So what we can do is we need to get the trajectory and light those motors before it does that, before it starts turning sideways. So let's kind of back it off to down like right there. So now we're at 12 seconds, which I can see down here in the corner. So instead of using 23 seconds, let's use 12 seconds. So we're going to go back to prepare for launch, and we'll go 12 seconds there, 12 seconds there, 12 seconds, 12 seconds. And now let's do flight profile and make sure that we go straight up. Okay, so look at this. We're going to get to 13,000 feet by having a longer delay between those motors. So the rocket took off. There's the first three motors. They burned out right there. It's coasting upwards, and we get to around 12 seconds. We should fire off those other ones. And now we're coasting upwards again, and we're going to get a higher altitude. Okay, and so now we're at 13,000 feet, and then the rocket's going to take forever to come down on its parachute. Okay, so let's look at that graph again. Yeah, let's plot that graph. Same thing. I'm going to change the color here, make it darker blue so we can see a little bit better. Plot the graph. Okay, so here's our thrust. So the rocket velocity came down. So now we're at 12 seconds. And then it started burning those other ones. And we got higher altitude. So if there was a process on maximizing the altitude, that's what you would have to do. But there are so many motor combinations that you could use. Here I have all of them are I-243s. The other thing, let's see if we can squeak a little bit more altitude out by changing, let's try a different motor. Usually, the motor that's going to give you the maximum altitude has the most total impulse. But sometimes you can get higher if the motor burns longer. So if we look at the burn time, this one is 1.69 seconds. This one's 2.2. That's better. Here's a 15.43 second burn. Let's try that one. Even though it has less total impulse, let's see what happens. So we're going to choose that H13 Super Thunder. That's what the ST stands for. And we'll make them plugged. And let's load all those motors. And we'll just launch it first to get a baseline. And it crashed. Oh, it didn't deploy. That's right, because we didn't have any. They're plugged motors, but it went 10,000 feet on 5H motors compared to 13,000 feet on 7 I motors. So now let's start doing that ignition delay, and let's start with 5 seconds for each of these, and let's kind of see what the graph looks like and the flight profile, and make sure that our rocket is still pointed up, because that's the big criteria here. And this is not a good sign. When the rocket is off to a corner right there, it typically means that it's arcing over. So let's see. So the rocket takes off, and see it's already arcing over, and we're going to lose a lot of altitude here because it instead of going up, it's going sideways. We have less thrust taking off, and it is going sideways. Yeah, we're not gonna get there from here. That's a fun profile though. Look at that, it's going sideways. Okay, click cancel. Okay, so what would we change here? Let's change those 3 of the motors. Let's make them I-243s. So the 3 in the middle, we'll make them I-243s. So I'm going to select those. Click OK. And then choose engine, I-243. Click OK. I-243, okay. So now we have in the motor, the ones in the middle are all I motors, I-243s, and then the 2 top and the 2 bottom are the H13s that burn for 15 seconds. So what we want to do is get the rocket pointed straight, and then 5 seconds after liftoff, those other motors ignite, and hopefully the rocket doesn't arc into the wind a lot and we can get higher altitude. So let's launch this and see what we get. We got to 11,000 feet. I cheated. I saw this 11,456 that we got to. So let's launch it here. So the rocket takes off on the 3 I motors. Now it's going to coast, and now those H motors ignite, and they burn and burn, and they're struggling. They're struggling. It seems to be lumbering up into the air. They're going to burn for 15 seconds. Oh, and then it didn't really coast at all. So something happened there. So let's see what happened. Oh, I see what happened. We got some motors with delays in them. So let's reset up that simulation. So this one had an ejection delay of 0. We'll change that to plugged. And then under flight events, let's deploy this at Apogee. So that we make sure we get to Apogee. Let's launch it again. Okay, so now I saw 13,000 feet. So we did get back up to 13,504. And we launch it. And let's see if it's going to coast. So the first 3 motors burned. Now the second 4 motors are igniting, and they're going up for another 15 seconds. It's struggling. It's lumbering up into the air. Okay, now it's coasting. And as soon as that's where it stopped burning out, and now it's coasting. And we're reasonably straight. Okay, so then we hit our apogee point right there, 13,000. So the process of maximizing altitude by doing air starting, again, what we did is we looked at the graph of velocity versus time, and we wanted this velocity to be as low as possible when we ignite those upper stage motors. But because of wind and weathercocking, as the rocket's going slower, the wind is affecting it and it's turning it into the wind. We have to make sure that it has enough velocity that the wind is not affecting it very much, so it still goes mostly straight up before we light those other motors. So here we're still at a pretty high velocity here. I bet you we could have probably maybe gone, probably as far out as 10 seconds to probably get a little bit more altitude. So let's try that. So let's, last one here. So we're going to change these delays to 10 seconds. And flight profile. I just want to make sure that the rocket doesn't start arcing into the wind before those upper stage motors ignite. While it's coasting, I want to see what the, we only got to 13,000. Those H motors, they just don't have very much thrust at all. And this is a big, heavy rocket. Yeah. See, now we're starting to arc, and because we're not going up, we're losing altitude. And so now, yeah. And that's where deployment is right there. Boom. Cancel. So again, we got to 13,253. So somewhere between 5 and 10 seconds on the delay, we'd probably get our peak altitude. So that's the process. It's not an automated process. It's more manual, and you have to know a little bit of physics. Like, I knew that I would get peak altitude if the velocity dropped down to 0. If the rocket remained pointed straight up. If the rocket starts arcing, then we need to move our delay to a smaller number to make sure that it's still pointed up when we ignite those upper, those air-started motors. Ron James says, or Johan says, oh no, Tim does a session at beer time again. It's a Friday night, about 10 o'clock in the Netherlands, and he's probably out at a bar. He's watching on his phone, probably. Carlos K says, Mylar and helium fins? Yes, Carlos, you could do that too. The procedure is you can go and create a new material and then make your parts out of that new material that has a negative density. So it is possible. Ron James Jr. says, is there a way to get an output DXF or DW for fin or nose cone layout? I'm building an upscale of the Estes Cherokee. Okay, so can you export out a DXF or DWG? So if you go to File and you go to Export, this is going to export the entire rocket. So if we want just a part, we have to go to the part itself. So go to the Rocket Design Components tab, go to the fin set, and this is not showing the button. There should be a button down right here that says Export Template. And it's not showing, and I'll show you how to turn that button on. So click OK. And you go back to the preferences. So under Edit, this is on Windows. On the Macintosh, it's under the Apple menu. Go to, what am I looking for? I'm looking for Preferences. Edit, Preferences, and go under, let's see, where is it at? Miscellaneous. There it is. Allow template exports. So make sure that is checked. And click OK. And then if you go back to the fin set, now you see down here it says Export Template. So if you click on that, here are our options. I can export out as an SVG or an STL or a CSV. STL is a 3D object, like if you wanted to send it to a 3D printer. SVG stands for Scalable Vector Graphics. So if I export out as a scalable vector graphic, and I need to tell it where I want to export it, and I want to do it to my desktop, and I'll export it out as a lock ultimate fin set and save, and then it tells me it did export and it's put it on the desktop, and it's lock ultimate fin set.svg, and then I'll click OK, and then I'll close this, cancel, save your changes, no, and then I'll minimize this and minimize that, and now I'm looking for that lock. I'm looking on my desktop for lock, there it is, ultimate fin set, and it's showing it as a Microsoft Edge document. To open this up, you need a drawing program. And let me open up Microsoft Edge. Where are you? There you are. And let's open up, what's it called? Inkscape. Normally, I use, I don't want images. Inkscape, go to download. Inkscape will allow you to open these. Download installer.exe format. Yeah, let's try that. Windows installer package. I don't know what that is. Let's try that. Download started. Okay, so it's 125 megabytes, and it's almost done. And we'll say open file and see what happens. Okay, and it's going to do the setup wizard. I accept the terms and conditions. I always hate these buttons. The icon. Next. Install. And it's going to install. So while it's doing that, so this is, if you're on Windows, this is probably what you're going to use, or you could use Adobe Illustrator, because those are vector formats. And then once you're in those, you can convert them to a DXF or a DWG. That's what I do. So hopefully, Ron, that answers your question. So the answer is yes, you can export out to create an enlarged version, but you have to do a conversion in the middle there, because it's going to export out, because the only format we have is SVG, but that's a vector format. And then in Inkscape or Adobe Illustrator, you can convert that to a DWG or DXF. Okay, it says it's finished. Inkscape, look at that. Put it on the desktop. I don't use Inkscape very much, so this is not a live stream that tells you how to use Inkscape. Okay, so that's kind of what it looks like. And if we do a file open, and if I look on my desktop, there's the lock ultimate fin set open, and it did open it. I hate this. So there's the fin, and then you need to reduce the magnification. So there's the fin, and then you'd probably do a file save as, and in here, yeah, see, I can do a DXF. There's a whole bunch of formats. I don't see DWG, but DXF was one of them that you asked about. Yeah, so that's that. That's what it looks like. So that's that fin. Johan says bread with peas and bacon. I don't understand that. Johan also says awesome flight. Now I really need to buy RockSim. Johan also says nice of this cluster, you can use 4 different engines and still have balanced thrust. Yeah. And Fat Bank says, yeah, that's going to be an expensive flight with all those 7 motors. And Johan says, I also built cluster in the same configuration, 6 by 18, 2 by 24, in a 75 millimeter body tube. Oh, he says, oops, 1 by 24. Fat Bank says, thanks, Tim. And I say, thank you, Fat Bank, for being here. Johan says, I have you in full stereo with subwoofer. Well, I don't have a stereo microphone, so it's mono. All right, so I'm out of RockSim questions. What time is it? Let's go back to RockSim. Where are my RockSim? There's my RockSim. There it is. So, yeah, this is another good episode here today. We're just almost at 3 o'clock. Let me just make sure I didn't miss any questions. That was it. You guys have been great today. Yeah, I feel strange. It's 3 o'clock almost exactly, and we don't have any more questions. Usually, last week we went about 20 minutes long. Fat Bank says, time flies when you're having fun. It sure did. So again, next week we are releasing the Black Brant rocket kit. And this is a 1/15th scale. We've already got them ready to go. We're actually ahead of. We're usually the day we release is we're still packaging things up, but we actually got it packaged up and ready to go. And I am so proud of my team. They did an excellent job. This was designed by Martin McKee. He's our product designer here now. I don't design as many rockets as I used to because just running the company is hard. It's just if I had to do everything, it's just not enough time to do it. So we've got a developer now, which is really cool. Johan throws in one last question: gap staging. And Johan, the answer is RockSim doesn't care. It doesn't know. It doesn't know that you're gap staging. It has no way of knowing. Venomous Predator Unleashed. That's a new name. What are your thoughts on adding BT-80 quick change motor mount to the Starlift Megalander? So let's open up the Starlift Megalander. Okay, so what I'm looking for here is on the Starlift Megalander, the quick change motor mounts they require a tube that's not blocked in any way by through the wall fin tabs. And on the Starlight, what I was looking for on this image right here is this has a through the wall motor mount attachment. So this fin goes into the body tube and it would block the quick change motor mounts from being able to slide in or slide out. So you could do it. You would have to modify these fins by cutting off the fin tab, but now you're doing a surface mount on the outside of the tube. Let's see if we got a picture here. Because what you worry about is landing. Because there's a lot of force when the legs are deployed. I got a picture of the legs deployed. I'm looking for a picture of the legs deployed. So on this picture, you see the legs here are deployed, but they're all attached. You can't see my computer. I forgot to turn the computer back on. I'm looking at it and you can't see it. So, but you basically you got the fins and then the legs attached to the outside, and there's a lot of, you got a large moment arm that's trying to, you got this force up here when the rocket lands. It pushes up. It's going to kind of want to tweak that fin. It's going to spin it into the tube, but still, I would worry about the fins popping off. Carlos says, hey, Apogee staff, tell Tim to share the screen. So there's this is the only picture I could find of the Starlift with the fins on the outside. Looking for that picture of the fins with the fin tabs. Okay, so this is the fin, and if you drew a line from that point to, actually it's this point to that point, this is the part that's inside the rocket that would prevent this quick change motor mount from sliding in and out. But if you took that off and you are willing to risk the fins snapping off because you have this huge moment arm when they deploy, it would work. Okay, I think that's all the questions. No. We had fun. I had fun. Thank you for coming. We will be back next week. Today is the 7th, so the 14th of April. We'll be back. Today's actually Good Friday, isn't it? So for you that celebrate Easter, happy Good Friday. And we will be back again next week, 2 p.m. Mountain Time Zone. That's 4 p.m. on the East Coast. And yeah, that's the only time that I had available in my schedule, so that's kind of how that happened. So until then, have a great week. Happy